This is the screencast for section 3.4, example 7. We're going to look at some derivatives in economics. A marginal is an economist's vocabulary for a rate of change in a derivative. So a couple examples you'll see here are there's a cost of production formula. Then the marginal cost of production would be the change in cost with respect to the level of production. You'll also see, actually right here is the revenue and then the marginal revenue, which would imply the derivative of the revenue. Example 7 says, suppose it costs C of X, so there's your formula for cost, dollars to produce 8 radiators when 8 to 10 radiators are produced. So in other words, for less than 8 radiators, it would follow a totally different function. For more than 10 radiators, a totally different function. I mean, there's a lot of other things to producing radiators than just a cubic functions worth of stuff. Like you need less employees, maybe you need a smaller factory, maybe you need less trucks. I mean, there's all these other things going on. Or maybe over 11, you know, if you are producing faster, you might have more injuries. I don't know, but this function will only apply for 8 to 10 radiators. Then R of X is going to be the revenue, so the income from selling X radiators. Your shop currently produces 10 radiators a day. Find the marginal cost and marginal revenue. So I've made an Algebra 2 kind of example of what's happening. We are producing 10 radiators per day, says the problem. So that is going to cost $550 total, and then we have 10 units, so that's $55 per unit. It is going to bring in, though, $820 or $82 per unit, which is a total profit of $27. Now, in the past, you've been asked, okay, how much would it cost to produce 11 radiators? And you would just plug in 11, and you would get $770 or $77 per unit, and then the revenue would be $1,100 or $100 per unit. That doesn't actually happen because this function, first of all, only follows this rule between 8 and 10 radiators, but also there is a rate of change that we can expect from knowing what happens at 10 radiators, and that's what we're going to explore here. So let's first find the marginal cost, which would be C prime of X. So the derivative of C would be 3x now squared minus 12x to the first plus 15. And then C prime of these 10 radiators would be $195, and that's per additional machine. Now the marginal revenue, R prime of X, is going to be 3x squared minus 6x plus 12. So the revenue for producing 10 radiators will be $252 per additional machine. So what this is saying is, using our marginal, the cost of 11 machines would be the cost of 10 machines, $550, plus $195, which would be $745 total dollars. And then the revenue of 11 machines would be the revenue of 10 machines, so $820 plus $252, so $1,072. So a little bit different than if we just plugged in 11 to our cost and revenue formulas. Our marginals are more accurate because they are giving us a rate of change to expect when we go on to this new piece of a function at 11 units. So graphically what we're saying here is, if I graph my cost function, this only applies to producing 8 to 10 machines. So only for this piece of the graph. Well, we're going to use the tangent line then, which is pretty steep, but we're going to use that tangent line to get the expected value of 11 machines. We're not going to follow this curve. We're just going to use what we think the rate of change is at 10 machines to predict the cost of 11 machines. Now this example comes with 2 now try problems. So here's the first one, marginal cost. So suppose that the dollar cost of producing X washing machines is this formula. Find the average cost of producing 100 washing machines. Not the average change in cost, just the average cost. So that means we're going to take the cost of producing 100 machines and we're going to divide it by that 100 machines. In other words, that's the total cost divided by the number of machines, which means the average cost is about $110 per machine. Part B, find the marginal cost when 100 machines are produced. Okay, marginal implies derivative, so let's take the derivative of C. Derivative of 2000 is 0, so then the derivative of 100x is just 100, x to the now 0, so I don't have to worry about that. Drop 2 down as a coefficient, so minus 0.2x to the first. Now I need to find the marginal cost at 100 machines, and I get $80. Now let's think about that for a second. Marginal cost is dc dx, and cost of x is total cost. So dc dx is going to be total cost, and then x is per number of machines, so per machine. So this would be $80 per machine is our marginal cost. So at producing 100 machines, our cost is increasing $80 per machine. Part C, show that the marginal cost when 100 washing machines are produced, so this C prime of 100 that we got, is approximately the cost of producing one more machine after the first 100 have been made. So remember, this is an estimate. We said cost of producing 100 machines was $11,000, and we think that the cost of producing 101 machines is going to be about, let's see, 11,000 plus 80, so 11,080. What this is saying, let's see if it actually is that amount. Let's calculate that directly. So let's do the cost of 101 machines. So I got $11,079.90. So we were off by 10 cents. One of those is off by 10 cents. So our marginal was 10 cents more than our following the cost function. So basically what we're saying here is the cost of producing 101 machines minus the cost of producing 100 machines determined by plugging that into the function is $79.90, which is about C prime of 100, and C prime of 100 is 80. So they are about equal. 28. Suppose the weekly revenue in dollars from selling X custom-made office desks is this function. Draw the graph of R, or use your calculator. What values of X makes sense in this problem situation? Well, the X values that make sense are producing more than 0 desks. You could produce 0 desks, I guess, so we'll say that X has to be greater than or equal to 0 desks. Part B says find the marginal revenue when X desks are sold. Wow, X desks. Say that fast 5 times. X desk. I can't even do it twice. All right, marginal revenue is the derivative of revenue. Before I take the derivative of this revenue, I'm going to distribute the 2,000, do a little algebra, see if I can make my derivative somewhat easier. Well, taking the derivative of 2,000 is going to be easy. That's just 0, but the derivative of this is going to require the quotient rule. See, in the denominator here I have x plus 1, so I can't just make that x plus 1 to the negative 1 and use the power rule because this is a whole function. It's not just the letter x. So here I go with the quotient rule. Again, the derivative of 2,000 is 0 minus, all right, in the numerator I've got the denominator times the derivative of the numerator. That's nice, that's just 0. Minus, now the numerator left alone, times the derivative of the denominator. Derivative of x is 1, derivative of 1 is 0, so that actually turned out a lot prettier than I wanted it, or than I thought it was going to. And then in denominator we're going to have the denominator squared. So simplifying here, that numerator turns into just positive 2,000. So r prime of x is going to be 2,000 over x plus 1 squared. That is the marginal revenue when X desks are sold. Now in part C, it says use the function r prime of x to estimate the increase in revenue, so the marginal revenue, that will result from increasing sales from 5 desks a week to 6 desks a week. So we're talking about an increase in 1 desk, which is what a marginal revenue will get us. The marginal revenue is going to get us the cost per additional desk. So I want to estimate R prime of 5, and that would be over 5 plus 1 squared. So I get that it would cost me $55.56, so $55.56. So this is an estimate of the increase in revenue. Now the total revenue would be if I plugged in R of 5 and then added this on. This is the increase in revenue from 5 to 6 desks. Part D. Find the limit of R prime as x approaches infinity. How would you interpret this number? Well, R prime, let's see, the limit as x approaches infinity of R prime, which is 2,000 all over x plus 1 squared. Let's see, I'm going to have 2,000 as a constant in the numerator, and I'm going to divide by a bigger and bigger and bigger number, so that is going to approach 0. So the limit as x goes to infinity, so as our number of desks goes to infinity, R prime approaches 0. So that means eventually I can keep producing and producing and producing desks, but I'm not going to make any more money. My revenue is not going to increase at all. It's going to stay the same. So I might want to say that as the number of desks gets very large, the revenue will no longer increase as more desks are produced.